Have you ever stopped to wonder how our planet stays, well, livable? It's getting hit with a ton of energy from the sun constantly. So how does it not just overheat, or on the flip side, freeze over? The answer is this really elegant idea called the Earth's heat budget.
So, let's kick things off with a little puzzle. We all know the sun doesn't hit the Earth evenly, right? The equator gets absolutely blasted with direct, intense sunlight, while the poles just get these weak, glancing rays. So, why don't the tropics just keep getting hotter and hotter until they boil, while the poles turn into permanent, solid blocks of ice? There has to be something going on that balances it all out.
To really get this, we've got to look at this fundamental imbalance first. It's kind of like a tale of two completely different climates living on the same planet. One has this massive surplus of energy, and the other is dealing with a major energy shortage. And here's the heart of the issue. Because the Earth is round, the sun's rays slam into the tropics at almost a 90-degree angle. It's like focusing a flashlight into one tiny bright spot. All that energy is concentrated, creating an energy surplus. But at the poles, those exact same rays come in at a really low angle, spreading the energy out wide and thin. That's what creates the energy deficit. This is where the hero of our story steps in, the Earth's heat budget. You can think of it like a planet-wide accounting system that is constantly and perfectly balancing the energy books to keep Earth habitable. So what is it really? Well, the heat budget is just this perfect balance between the energy coming in from the sun, that's called shortwave radiation, and the heat the Earth sends back out to space, which we call longwave radiation. The golden rule is simple. For the planet's temperature to stay stable, the energy coming in has to equal the energy going out. That's it.
To make this super clear, let's just pretend that 100 units of energy from the sun show up at our doorstep, right at the top of the atmosphere. We're going to follow every single one of those units and see exactly where it goes. It'll show us exactly how this whole balancing act works.
All right, welcome to the Energy Accounting Department. Let's start tracking the planet's income and expenses. Okay, so right off the bat, of those 100 units that arrive, 35 of them are immediately reflected straight back to space. They're gone. This reflection is what's known as Earth's albedo, and it literally plays no part in heating the planet. So that leaves us with 65 units that are actually absorbed by the Earth system.
And just real quick, where's that reflection coming from? Well, clouds are the big one. They bounce back 27 units all by themselves. The atmosphere scatters another 6, and bright, shiny surfaces like snow and ice on the ground reflect the last 2 units.
Now, let's get back to the 65 units that actually stick around. This is where things get warm. A huge chunk of it, 51 of those units, is absorbed directly by the land and the oceans. Only about 14 units are absorbed by the atmosphere as the energy is coming in. And this is absolutely crucial to understand. The atmosphere is mostly warmed from below. The sun heats the ground, the rocks, the water, and then the ground radiates that heat back up, warming the air. This one idea is the key to understanding everything from a simple breeze to massive global weather patterns.
Okay, so quick recap. The Earth system has absorbed 65 units of energy. Now, to keep that perfect balance we've been talking about, it has to send exactly 65 units back out to space. No more, no less.
So how does it do that? Let's follow the numbers on the outside of the ledger. The Earth's surface radiates a whole bunch of heat, but only 17 units make it directly out to space. The other 34 units get absorbed by the atmosphere on their way out. Now, the atmosphere has its own heat to deal with, right? It's got the 14 units it absorbed on the way in, plus the 34 it just grabbed from the surface. That's 48 units total, which it then radiates away into space. So let's do the math. 17 from the surface plus 48 from the atmosphere, that equals 65 units out. The books are perfectly balanced.
So the overall budget is balanced. That's great. But what about that first puzzle we talked about? The tropics still have way too much heat, and the poles don't have enough. Well, that very imbalance is what drives the planet's massive, incredible climate engine. You know, this quote from the source material really just nails it. The planet has this built-in redistribution system. It's constantly and actively moving heat from where there's a surplus to where there's a deficit. This constant motion, this circulation, is what gives us our climate. And this happens in two main ways. First, you've got the atmosphere. Think of it as the real workhorse here, doing about 75% of the heavy lifting through winds and big weather systems. The other 25% is handled by the oceans. They act like these giant, slow-moving conveyor belts, carrying enormous amounts of heat from the equator toward the poles in their currents.
So why should you care about any of this? Because this giant global process isn't abstract at all. This heat engine is directly responsible for the weather you see right outside your window every single day. Let me show you how.
Literally every major factor that defines your local climate is a direct result of this system. Where you live, your latitude, determines your baseline for solar energy. The prevailing winds, which are driven by this global heat exchange, are what bring warm or cold air to your region. And if you live near an ocean, those currents we just talked about can make your home way warmer or cooler than other places at the exact same latitude. It all connects.
So, when you boil it all down, the Earth's heat budget isn't some boring, abstract concept from a textbook. It is the powerful, invisible engine that's working 24/7, creating the winds, the currents, and the pressure systems that eventually become the weather forecast you check on your phone every morning.
Our planet's climate is the end result of this unbelievably complex and delicate dance between energy coming in and energy going out. And that has to leave us with one final and pretty important question to think about. What happens if we start to tip those scales?